Welcome everyone to Lecture 2B, where we're going to be talking about heats of vaporization and how they relate to the Clausius-Clapeyron equation. So we looked earlier at the Maxwell-Boltzmann distribution for molecules at various temperatures. And what we saw is that there's always some fraction of molecules that have enough energy to escape a surface, particularly molecules escaping as a gas from the surface of a liquid. And what this leads to is the idea of vapor pressure that we looked at in previous lectures. Now, if we have high vapor pressure materials, we call them volatile. Examples of that might be something like acetone or gasoline or hexane, or things that you tend to smell very easily because they have a very strong odor coming off of them. Things that have a very low vapor pressure we call non-volatile. Something like water you might consider to be non-volatile. Well, here's a very rudimentary Maxwell-Boltzmann distribution of thermal energy here, where you have your fraction molecules on the y-axis and kinetic energy on the x-axis there. And we see down in here that even though at a lower temperature you have fewer molecules with enough kinetic energy, you still have a certain amount of molecules. So if we just look at that area underneath, it tells us how many molecules have enough energy to escape the surface. And if we go up to a slightly higher energy here in red, we can see that that area is quite a bit greater and so we would expect it to be more volatile. If we were to really zoom in on this equation, and of course we can't here because it's not dynamic, but even for that cold temperature, we would see that there is still a area under the curve all the way out because it is an exponential decay and it never actually reaches zero. So if we kind of keep all of this in mind and we think about the amount of heat that's needed to convert a single mole, 1 mole of a liquid to gas, we call that the heat of vaporization. And so we just put a little subscript label on delta H enthalpy, and it's a delta H vape. It's also the enthalpy of vaporization is another very common way of seeing that. Normally, we would give the heat of vaporization at the boiling point, but if you change the temperature, you're going to have a different delta H of vaporization. But for normal reporting, we do report that at the boiling point. And so for something very common like water, if we look at the amount of energy needed to take water liquid at 100 degrees Celsius and turn it into water gas at 100 degrees Celsius, we see that we get an enthalpy of vaporization of 40.7 kilojoules per mole. So that's how much energy needs to be absorbed by the water molecules in order to break those hydrogen bonds between water molecules and turn them into independent molecules of water gas. And so all we've done here is change the phase of our water. We have not changed the temperature. It's water liquid at 100 going to water gas at 100. The energy is strictly to break those forces. Now, if we go in the other direction, if we're taking water gas and condensing that to water liquid at 100 degrees Celsius. So here, this is the energy that's going to be released when those hydrogen bonds reform. And so it's just going to be exactly the opposite. We could call this the heat of condensation if we wanted to. I don't think that's a normal label, but you can certainly call it that. We see that it's the exact same amount of energy, only now it's negative because heat has to be released, and so it's an exothermic process. This is actually a considerable amount of energy, and if any of you have ever had a steam burn, you would understand that that is a lot of energy going into your hand, which is why a steam burn heats or feels a lot worse than just sticking your hand in boiling water. So let's get back to this idea of vapor pressure. So vapor pressure does represent a dynamic equilibrium between the liquid and the gas. It's the reason that at a certain temperature, there is a very specific value for the vapor pressure. So you don't have more and more molecules just continuously evaporating. If you have a closed system, you have molecules evaporating and recondensing back into into that liquid as we see here. If you have an evacuated cylinder, as you do here, with no gas molecules present above the surface of the liquid, all of those molecules are going to come off here. As we're not quite at an equilibrium yet. We still have more molecules coming off the surface of the liquid, and any of the ones that are already in here do have a chance of recolliding with the surface and sticking back to other liquid molecules. But then we still have more coming off here. Eventually, you have the exact same number, and you can kind of count the arrows here. We have 3 molecules coming off the surface, 3 molecules coming down out of the vapor, and so we create that dynamic equilibrium. So the rate of evaporation becomes equal to the rate of condensation at that equilibrium. So once that system has reached equilibrium, you do still have vapor pressure, and it's unchanging. And so here, if we kind of compare where we started here, where we had no molecules above the surface of the liquid, as more and more molecules come up or enter the gas phase, your rate of condensation becomes the same. If you look at the vials there, they have the same number of molecules coming off the surface. That never changes. That's based strictly on that Maxwell-Boltzmann distribution, based solely on temperature. So your rate of evaporation never changes, but what happens is that your rate of condensation rises and matches your rate of evaporation. So once those two things are equal, you have your dynamic equilibrium. Let's talk about dynamic equilibrium. We talked about it a little bit in our introductory chemistry course. So if we have a dynamic equilibrium, it's a condition that will reestablish itself if it becomes disturbed. And we talked about it more in terms of reactions, but we can also look at it in terms of phase changes. And so in this example here, we have a piston, the space over a liquid, a volatile liquid, and here we have a liquid here. We have some of that liquid evaporating, we have some of that vapor condensing, and so here we have an equilibrium situation here. Now, if we go ahead and raise that piston, we have now changed the conditions inside of this container. We have decreased the pressure, we have increased the volume, and so what's going to happen is that more gas molecules now have space to move around here, and notice the size of the arrow of those evaporating is exactly the same because that's based solely on temperature. But what happens inside the vapor is they have more room to move, and so they don't collide with the surface quite as often. And so you have more molecules that can occupy the space up in here because you have fewer collisions with the surface until you get more molecules up in here. And so you're going to have a little bit higher vapor pressure at that lower overall pressure. Now, if we go the opposite way and we go down, we increase that pressure by decreasing the volume, then there's not as much space in here for those molecules to move. They're going to collide with the surface of the liquid more often. You're going to get more condensation initially. And so eventually you're going to have fewer molecules in the gas phase, so you're going to have a lower vapor pressure there. So if we compare the ideas of vapor pressure and boiling point, it doesn't seem like they should be linked, but in fact they are very strongly linked. So if we think of boiling, we think of a boiling point temperature. We think that that's where we have taken a liquid, we've put enough energy in it to where we break those bonds and turn them into a gas phase. Well, that's what vapor pressure is taking those liquid molecules and turning them into a gas phase. So boiling occurs, the boiling point occurs when the vapor pressure of a liquid is equal to the external pressure, so like the atmospheric pressure. Normal boiling point is where the vapor pressure is equal to either 1 bar or 1 atmosphere, depending on the tables that you look at. And we see here we have a few various liquids here. Diethyl ether has a boiling point of 34.6. So here we're tracking the vapor pressure as we go up. So here, this graph, this is actually 1 atmosphere of pressure. And so diethyl ether reaches 1 atmosphere of vapor pressure at 34.6 Celsius, so just a little bit above room temperature. So if you hold, this is below body temperature, so if you hold diethyl ether in your hand, it evaporates quite rapidly. If you look at something with a little bit higher intermolecular forces, ethyl alcohol, ethanol, has a boiling point of 78.3, and you can see the vapor pressure as you change the temperature is quite a bit lower than diethyl ether, but it does have a boiling point of 78.3. And then when you get to water, water has a fairly low vapor, very low vapor pressure actually, and it rises slowly until you get to 100 C. Here, much slower than ethyl alcohol, so you get out here to 100 C. And then out here we have ethylene glycol. You can see its vapor pressure is extremely low. It's a fairly large molecule. It does have two OH groups on there, so it's got two locations possible for hydrogen bonding. So the molecules can really bond to each other quite strongly with intermolecular forces. Ethylene glycol is what we use for antifreeze, or used to be what we use for antifreeze in our vehicles, and it's because it does have a fairly high boiling point, and you mix it with water and it drives the boiling point up even higher actually, and this is the reason why, is because it's very fluid, but it has a very high boiling point, and it's easy to have a very low freezing point as well, and so it serves as your antifreeze as well, and it keeps the coolant in your car from freezing during a cold winter. And so we mentioned that the boiling point is equal to where your vapor pressure is equal to the external pressure. Well, if the external pressure begins to change, then your boiling point is going to change as well. And we can look at that with elevation changes, because as you know, if you go up in elevation here, your atmospheric pressure begins to change. So if we look at the extreme here, the top of Mount Everest, the approximate pressure is only about 0.32 atmospheres, so that's going to be fairly close to the same value for bars. Very low. You're about a third of your normal atmospheric pressure, and the approximate boiling point of water is only about 78 degrees Celsius, so it's fairly low. As you come down to Mount McKinley in Alaska, 0.46 atmospheres, is still less than one normal atmospheric pressure. You're at 83. Mount Whitney, 87. Denver, Colorado, which I used to live here. It's at 1 mile. That's 1 mile high, or 1.6 kilometers. You're at 0.83 atmospheric pressure, and boiling point of the water there is 94. And then if you go to somewhere that's near sea level, like Boston, 20 feet above the sea level elevation, or about 6 meters, your atmospheric pressure is essentially 1, and you expect your boiling point of water to be right at what we expect, 100 degrees Celsius. So I mentioned at the start that we were going to look at something called the Clausius-Clapeyron Equation. And what the Clausius-Clapeyron Equation does is it allows us to see how the heat of vaporization, or how the vapor pressure of liquid will change based on the heat of vaporization and different temperatures. So if we look at the equation, it's not going to be a very nice equation because it's not linear. However, we are going to be able to put it into a linear form, which means that we can graph things and plot and find some other values if we need. So here's what we call the one temperature form of the Clausius-Clapeyron equation. So we have the natural log of P vaporization. So this is the vapor pressure of a liquid. And it's going to be equal to the negative heat of vaporization divided by R. Now, you may wonder which value of R we're going to use here. Well, delta H is a enthalpy, so that's going to have a joules per mole type unit, and so we're going to want to use the R value that uses joules. We have 1 over T. Of course, T here must be in Kelvin, otherwise at 0 Celsius we run into an undefined equation. And then, of course, we have here this little natural log of beta, and this is where some of the problem becomes in, because what's beta? And I'll be honest, I don't know what beta is. This is in kind of a y equals mx plus b, so it is in a linear form here. However, we don't know what that value is. Now, if we go through and measure vapor pressures of a substance at different temperatures, we could plot those and actually find this value of beta. And so if we plot that out here, you can see we get data. And this would be like real data where it kind of meanders a little bit. It's hard to get exact data. We can find here that we have the slope if we go back and look at our equation here. Real quick, there we go. We can see that that's our m, our x would be 1 over t, y would be the natural log of the vapor pressure, and that becomes our y-intercept. So now if we go back to the graph here, we can calculate the slope by measuring at different points. We have our 1 over t here, our natural log of vapor pressure here, and you can use whatever value or units you want for your vapor pressure. It just changes some of the values that are in here. So if we take our negative slope, and if we look back at the equation, we saw that our slope was actually heat vaporization divided by R. So if we wanted to find the heat of vaporization, we need to find the slope and then multiply by R here, 8.314 joules per Kelvin mole. And we get 28.92 kilojoules per mole for the vapor pressure. So that's a little bit of a complex way to go. One of the most common ways that we use the Clausius-Clapeyron equation is what's called the two-point form. And in the two-point form, what we're doing is we're just taking two temperatures and two vapor pressure measurements, and we can manipulate them algebraically so that we get the natural log of P2 over P1. So these are our two vapor pressures at the two different temperatures. That's going to be equal to, we still have our negative delta H vaporization over R, and then we have our 1 over T2 minus 1 over T1. And when we solve that, if we know the vapor pressures, we know the temperatures, we know R because it's a constant, we can solve for our vapor pressure directly rather than having to make several measurements and make a plot. So this also removes that constant beta from the equation. We don't have to worry about it anymore. Well, that finishes out lecture 2B. Thanks for sticking through it. Please move on to lecture 2C.